Good evening, everybody, and thank you for joining us tonight for the 10th meeting of Quantum Serbia Initiative. We have a lot of people in the audience already, so I will ask you all, if you haven't already, please join us in our LinkedIn or meetup group so that we can all learn together and advance in the field of quantum computing in Serbia. It is really a great honor and privilege for me to welcome tonight Dr. Marko Rančić, who will give a talk regarding some applications of quantum computing in the energy industry. Marko had a very interesting path to the position he holds today. He is now a permanent senior researcher in one of the largest companies in the world, company Total Energies. He obtained his bachelor and master's degrees in physics in the University of Niš in 2010 and 2012. And his PhD at the University of Constance in Germany in 2016 under the supervision of Professor Guido Bucart. Topic of his research was coherence and control of semiconductor qubits. After that, he continued his academic journey at the University of Basel in Switzerland under the guidance of King Faisal International Prize winner, Professor Daniel Loss, where he worked on nanowires for quantum computing applications in spin and topological qubits. And today he's responsible for managing multi-million euro research budget in quantum computing with dozens of researchers working on different aspects of quantum hardware and software. So just a quick reminder before we start, if you have any questions during the talk, you can type that in the chat and I will read the questions to Marko after he finishes. And the other alternative would be that you raise the hand after the session and then you can ask the question live or discuss. So once again, thank you, Marko, very much for sparing some time for us tonight. And please present your work.
Thank you so very much for the invitation and for the nice announcement. To just share the screen slideshow, play from start. Okay, everybody sees the slides. Slides are ongoing. So yeah, thanks for the invitation. What I prepared here, I prepared kind of a balanced type of a presentation. So it's going to start with a broad overview of what quantum computing is, but I won't spend that much time on that. I won't say this is a qubit and you do this with a qubit, because I believe that you already saw a fair share of talks. So I'm more going to focus on the current problematics, current state-of-the-art hardware, current state-of-the-art software, and how do you play with these things and how do you combine all of these things together. And then the idea is for people who really have a more technical angle to the story, to give kind of in-depth overview on one scientific topic. So there's going to be a part of the talk which is going to be kind of a pure science, which you would see in a short 10-minute talk on any conference. So as you heard, I'm Marko. I work for Total Energies since 2019, and Katarina has said something a bit about the path, which led me here. And let me tell you how this looks from my aspect. So back in 2019, I was living in Switzerland at the time, and I saw an ad that Total at the time, which was the name of the company, was looking for a group leader in the domain of quantum computing, and I had absolutely no idea what Total wanted to do with quantum computing. And I thought it was a semi-joke, the job. And so I applied for the job. And then, I slowly started learning that Total had a long history of high-performance computing. At the time when I joined Total in 2019, Total was in a possession of the largest supercomputer available to industry. So this
Marko, excuse me, we can't see your screen, your slide.
My slides?
Yeah, we can't see it.
Yeah, we still see Sasha's screen. Maybe he needs to stop sharing.
Okay.
Yeah, I think you need to stop sharing.
Okay.
Yeah, okay. Now it's
okay
done.
now.
Okay, do you see my slides now?
Yes.
Perfect.
Okay, I'm still on the title slide, so didn't really miss anything. So what I was saying that Total has a long history of Total at the time, now we're Total Energies, has a long history of high performance computing. That at the time when I joined, our Pangea supercomputer was the 11th most powerful supercomputer in the world. And it was the largest supercomputer, the most powerful one available in industry in general. So why do companies like Total use high performance computing to start with? Where in the old days when we were still kind of an oil and gas company, Total was really using it to model things like subsurface research. Now, since last year and this year, Total is really moving away from carbon emitting energies. We announced our motivation to kind of be a broad scope energy company, and we apply more quantum computing into quantum computing and high performance computing, because we're still a big topic of our research in basically low carbon energies domain. And the quantum computing, it's kind of a continuation of computing technologies which were developed. First, you had HPCs, then these are high performance computer. Then people started working a lot with GPUs. Then for those of you who are not in this high performance computing field, GPUs is a graphical processing unit. You basically use a graphic card to run certain types of computation. And then, everybody asks, you have the CPU, the GPU, what is the next step? Well, the next step is the QPU, is the quantum processing units. I saw some estimations that pretty much 50% of all of the large corporates have their own research teams in quantum computing. Some take a more research aspect to the problematics. Some take a more, I would say, investment approach to the problematics. So you can find different strategies. But what I'm presenting really here is everything which has to do with research in quantum computing. Every talk with quantum computing kind of starts with qubits and what qubits are, and I didn't want to dwell too much on it, but maybe for people who are first time seeing any talk related to quantum computing, if such people are maybe in this call, how classical computers work. They are composed of classical bits. They're zeros and ones. So you're all sitting on a PC or a laptop, or maybe somebody on a tablet, and such machines have their own processors. And what these processors are is they're tiny, tiny wires for which electricity runs or doesn't run. If the electricity runs for this very, very tiny wire inside your laptop, then your kind of a bit is in a state of a 1. And if an electricity doesn't run, then it's in a state of 0. And quantum computers, they don't follow the same logic. In a quantum computer, there is this exotic state called the superposition. And you probably all heard about this Schrodinger cat's paradox, where a cat is basically dead and alive. And qubits really exploit this property. Qubit stands for a quantum bit. It can be in a 0 or 1, but it can also be simultaneously in a state of a 0 and a 1. And this is the famous quantum superposition states in quantum mechanics. But this is not where the quantum speedup is really coming from. And a lot of time when people speak about it, they don't really realize where quantum speedup is coming from. For the quantum speedup, you need another phenomenon. And this phenomenon is called entanglement. Entanglement is in a way a consequence, I would say, of superposition, or maybe better, that the superposition that superposition is a prerequisite of the superposition is a prerequisite for quantum entanglement. And what is quantum entanglement? It's one of the most fascinating phenomena in nature. This means that two objects can be correlated in a way such that the state of the object 1 influences the state of the object 2. Now imagine that my hands were correlated, and imagine if I told you, okay, these two hands, they're a pair of the same person. You would only need to see the left hand to be sure that the other hand is the right hand. And if you take this into technology and make quantum bits out of it, same logic would apply. If you entangle two quantum bits, if the state of the first quantum bit is a 0, you would be certain that the state of the second quantum bit is 1. But this is still not what allows quantum computers to be powerful. What really allows quantum computers to be powerful is if you take the first bit to be in a 0 and the second bit to be in a state of 1, and you entangle them. By flipping only the first bit, because they're entangled, the second bit would follow automatically. And now you take and you make a network of million such quantum bits, and you only need to operate on one of your bits and flip it and change its states. And because of the quantum entanglement itself, all of the other quantum bits would follow this operation. So these are correlation capabilities which don't exist anywhere in the classical domain, anywhere with a CPU, and anywhere with a GPU or any other type of computer. This is why quantum computers are so powerful. Okay. You know, I wanted to kind of give you a timeline of the development of quantum hardware and what quantum computers are good for, because people call everything today a quantum computer. You know, if somebody heard of D-Wave, they say D-Wave is a quantum computer. D-Wave is not a quantum computer, it's a quantum device of a sort. But D-Wave is the first device which was ever commercialized. Now we're already, D-Wave 3 has been announced. What D-Wave is a device which is called quantum annealers. It's kind of relies on an effect called quantum tunneling and finds basically a solution to a binary optimization problem. So it's kind of a specialized device which is specially made to solve one problem in operational research, but only because it's a device which is specially made to solve one problem. This doesn't mean that it doesn't cost 10, 20, 30 million dollars, because the problem which quantum annealers such as D-Wave solves, it's a really complicated problem. Then you have what is currently called NISQ quantum computer. What NISQ means, it means noisy intermediate scale quantum computers. What they are quantum computers of today. So if you saw the Google announcement of quantum supremacy, the quantum supremacy was achieved with the NISQ device. It solved the problem which was untreatable to any classical computer at the time. This is type of the quantum computers which IBM has, this type of quantum computers which Google has, which some smaller companies like Rigetti, for instance, or IonQ have in their dilution refrigerators. Then there is something which is maybe the most exotic device in my kind of book. This is called the Gaussian boson sampling machine, and this is namely used for machine learning type of purposes. What is a Gaussian boson sampling machine? Well, it's a kind of a neural network made out of lasers, and these lasers kind of make an interference pattern, with the lenses. And when they do so, the kind of interference pattern which you get on the screen is telling you something about the kind of the initial problem, the system you study. So for instance, you can encode a vibronic spectrum of a molecule into such optical neural network, so to say. You can set your lenses and prisms to kind of reflect some particular properties of a given molecule, and then you get an interference pattern on the screen which is giving you a vibronic spectrum of this given molecule. And then there's the fourth type really of quantum devices, which is something called a universal quantum computer. They don't exist. You see them in the timeline. What is a universal quantum computer? It's a NISQ device which has quantum error correction implemented on it. And I'm going to tell you briefly what quantum error correction is. Classical computers make errors all the time. You don't know it because it's in the depth of your processor. And how classical computers compensate for errors, they compensate by making kind of obsolete copies of the same process. Imagine you had one bit on a classical computer and you do some operations at it, and you want to make sure that this bit at the end of this set of operations is in a state 1. How you will do it on a classical computer, we make 2 more copies of this bit. And then if one of these 3 processes had an error, then there's going to be a majority vote. The 2 remaining bits were in a state 1. However, this doesn't work like this for quantum computers. And the biggest challenge today in the domain of hardware is kind of taking quantum error correction schemes, which exist there, and really trying to implement them on current day devices. This is what the next decade or maybe even 2 decades in the development of quantum computing is going to be all about. It's going to be all about quantum error correction. Why do people, and I have a bunch of scary formulas here, but I'm going to try to help you understand what these scary formulas mean. And if you don't have a computer science background, this is going to be a bit tricky for you, even if you're a mathematician or a theoretical physicist, if you're not familiar with the big O notation. What am I showing here? I'm showing classical runtimes as compared to quantum runtimes. And maybe the best example, which I can give you for this, what this figure means, is database searching. Imagine I gave you 100 numbers distributed from 0 to 100, okay? So, sorry, from 1 to 100. And imagine that these numbers are randomly distributed, meaning I give you a realization and it's 42, 51, 76. Then I give you another random set of the same number, 1, 17, 26. Then I give you another random set of this number, 51, 29, 53, right? And so on and so forth. And I ask you to find a very, very specific number. I ask you to find the number 10 in this list. So sometimes in this random generation, the number 10 is going to be at the first place. Sometimes in this random generation, the number 10 is going to be on the last place. In average, it is going to be at average, you're going to need n-half searches for this database to find where the number 10 is kind of located in this random list of numbers. So this is why you say that the classical database searching scales like O to the power of n, where n is basically 100. It's numbers from 0 to 100. So this means you need to go and search for your database close to a number which is proportional to the number of entries. So 50 in principle. However, on a quantum computer, you can do this search of a certain entry in a randomly distributed database in a square root of n times. You would just have to search n times, or sorry, you just have to search 10 times for your database to find where is the number 10 located. You have to search 10 times from 0 to 100, randomly distributed numbers to find where the number 29 is located. And this is the magic of quantum computing. This is what is called, quantum advantage sometimes. And the same applies for problems in cryptography. Basically, if you want to solve a problem in cryptography, you would have to ask the question to the computer 1,000,000 times. However, on a quantum computer, you just ask it a logarithm of 1,000,000 times. These are the so-called universal algorithms which exist, but they're not implemented because they require quantum error correction to be implemented. And then on the bottom, you have the so-called NISQ algorithms, which everybody's doing now, from IBM to Google to Microsoft. And they're only beneficial for chemistry and optimization type of problems. They don't really have a speed up like kind of a smaller runtime, but they allow you to really represent problems which are difficult to represent on a classical computer, on a quantum device. This is the best way in which I could explain this. Okay, main problems with quantum computers today. First, record device has 65 qubits. I think IBM holds record. I think Google has 64, IBM has 65. So we don't know how to make a lot of qubits. We can make very few of them. And even when we do, and this is the second figure, they're not well connected to one another. In an ideal setting, in an ideal world, you would need to have all-in-all connectivity between your qubits. What does this mean? This means that every point in my processor is directly coupled to every other point in my processor, but this is just not the case. What you're seeing here, you're seeing something called the chimera graph of D-wave. Third problem, which is an important one, but being a theoretical physicist myself, until recently, I never realized that this is a problem, and this is wiring. What's this thing with wiring? What you're seeing here, you're kind of seeing how a dilution refrigerator looks like. Quantum computers work on a temperature close to absolute zero. You need a really, really, really big refrigerator to cool a chip, a sample close to the absolute zero. And then all of your control electronics, which you use to control your quantum computer, is going to be on room temperature. So you have to think of clever solutions in which you take room temperature electronics and make it functional at temperatures close to the absolute zero. And on top of that, ideally, you know, you want, if you want to have million qubits, this means you need to put a million cables and cool down million cables of temperatures which are really close to the absolute zero. So it's a difficult, if you want, engineering challenge. And the last one is really quantum noise, but this I already spoke about, the fact that we really don't have error correction, that our qubits are similar to classical qubits, imperfect, that they make errors, and that we don't know how to correct such errors. I just wanted to kind of to give you a provocative slide to show you how how quantum computers really look like. So a quantum computer is this black small thing, which you see. This is the chip holder. And then this entire part is kind of synced into a refrigerator and cooled to the temperature of minus 273 Celsius. And what you're seeing here, these are these Gaussian boson sampling machines. These are this optical neural network. This is on the right-hand side, if you see my cursor, and I hope you can, the D-Wave device. And here you see kind of, you cannot just cool a sample simply to a temperature close to absolute zero. You have some stages of cooling. And in the end of the day, basically quantum computing just occurs at the very, very end of this kind of cooling stage. Last but not least, I put a picture of the machine which we have in-house. This is not an actual quantum computer, it's a simulator of quantum computers. So we bought one of these machines from Atos, who is our premium partner. And I have this machine located in our research center in Pau, which is in the south of France. And what my team is doing, my team is really working and developing algorithms on these quantum simulators, testing them, and then going to actual devices and seeing how do I develop algorithms from a simulator scale on an actual device. This is the game, and this is because the actual devices are really pricey and difficult to get hold of. What I wanted to show you maybe a bit, I wanted to show you kind of an example of, you know, if you're scared and you heard about quantum mechanics and you think this is really not for you and this is not something you can do. I just wanted to show you how a code of a quantum computer looks like. On the left-hand side, you have IBM Atos's MyQLM, which is the language that we mostly use in Total, but we also use the one on the right-hand side, which is Qiskit. So if you know anything about coding, you probably heard about Python. If you heard about Python, this is how you code modern quantum computers of the day. You can install a number of compilers of quantum computers: Google Circ, Atos's MyQLM, IBM's Qiskit, Xanadu's PennyLane and Strawberry Field, and so on and so forth. And really on your laptop, simulate what small quantum circuits would do. And what you're seeing here, you're basically seeing a very simple 1-qubit quantum circuit and a very simple 2-qubit quantum circuit on the right-hand side. So it's difficult. Quantum mechanics can be scary, especially if you're not trained as a, applied mathematician or a theoretical physicist. But, you can still kind of have a high level, pretty kind of high level front end, which allows you to play with quantum computers, though you don't even know much about what is really happening at the processor level. And this is similar to what we have today in classical computing, because when you use the classical computer, you don't really know what kind of semiconductor electronics goes into it. You just turn on, Fortran, Python, C++, and you code. So this is kind of a bit of a similar idea. Now what I wanted to show you, what we work in Total. So now I kind of finished the broad. I have to check how am I doing on time. I'm mistiming the talk totally. I took too long on the introduction. So I'm gonna speed up, I would say, a bit. So what we do at Total, we do modeling and optimization. We solve equations for physics. We model chemical system and materials, and we combine different types of quantum hardware and quantum software. And really, the ambition is, and where we really want to use quantum computing, we really want to use it in our novel carbon neutral business. And we're sure quantum computing is going to be a game changer, but there are many problems in using quantum computing, even for a company like Total. First, most of the people in our numerical departments don't have competencies in quantum computing. Second, applications are a bit unknown. Third, we really don't have too much visibility. We're not a computing company like Google, for instance. And third, we really don't know in which domain are these new type of computers which are being developed going to be applied. This is kind of the first list of challenges in chemistry and materials. And where we use them, where we namely use quantum computing, we use it in battery materials, and we use it in modeling metal organic frameworks for CO2 capture. We don't have really too much going on at the moment on catalysts for CO2 conversion. And this is everything is in the NISQ domain, so noise intermediate scale quantum computers. Second is in modeling of optimization. What you have in any kind of big company, you have trucks going from point A to point B. You have a network of vehicles, which you kind of need to optimize to consume least resources and bring maximum profit. And we also use quantum computing in the domain of oil and lubricant blending and fuel blending and biodiesel blending. So this is the type of problems that we are treating with quantum computing. And we have least maybe of everything which I showed here in the domain of partial differential equations. Why is this the case? Why do we have so little on partial differential equations? Well, for practical reasons, state-of-the-art algorithms for quantum computers are pretty bad in the domain of partial differential equations. The technology is not yet. We cannot do wave propagation or lubrification or combustion modeling with quantum computing. Best what we can do, we can try to treat very simple linear algebra problems on current day devices. And last but not least, we have ongoing interactions with pretty much all types of hardware and software vendors. Our premium partner is probably Atos, which is a French company, and we combine a number of software packages with a number of different quantum hardware. And this is kind of, here you kind of roughly see the team who are the people who are involved. So it's namely PhD students and postdocs, also interns here or there come and go. And my project has two advisors, Jean-Philippe Picmal and Yvonne Madej, who's a chemist and mathematician, respectively from the Sorbonne. Why do I have advisors? So I realized pretty early on that although I know a fair share about quantum computing, I do not know which problems are difficult for chemists. And I do not know which problems are difficult for applied mathematicians. So I really needed some help in a sense that I needed somebody to say, okay, this is a really difficult problem in chemistry. And this is why we have this amazing really group of researchers working with me and Total and kind of supervising PhD students and postdocs together with me. This is probably our key focus, but I'm not going to give a deep scientific dive on this key focus for the following reason, because we're writing a paper and the paper is not ready yet. What you're seeing here, you're seeing a unit cell of a material which is called the metal organic framework. What this material has, it has metals. These are these red things, which you see here. It has benzene linkers. These are these kind of black hexagons, which you have here. And this large gray ball, which we're seeing, is empty space. So why do we use these materials? Why are they so important for us? Because we hope to use them as kind of sponges to absorb CO2 from exhaust gases and to reduce CO2 emission. Why is this such a difficult problem? It's a difficult problem because one unit cell of this material has 144 electrons. So it's impossible to treat this kind of fully quantum mechanically. And this is a problem where approximate solvers, such as density functional theory, are known to give non-physical results. So in a sense, there's an actual need to have a really precise model of CO2 molecule interacting with the metal organic framework. And on the other hand side, most of the classical methodologies which we are applying don't work here. So this is, close to 2 years ago, we embarked on a project with a company from the UK called Cambridge Quantum Computing. They were a startup, but you know, the startups in quantum computing quickly stop being startups and become large companies. So I would say they're a medium-sized company at the moment. And what Cambridge Quantum Computing is helping us do, it's helping us basically to develop strategies. What is the best way how to tackle this type of problems with quantum computing? So current quantum computers cannot treat such large molecules or materials. So this is why Cambridge Quantum Computing is helping us develop fragmentation strategies. And you kind of split this material into smaller fragments, and the active site in the material is treated with quantum computing, and all of the kind of remaining site of the material, which are not that important, are kind of treated with the mean field methodology, which is pretty cheap on a classical computer. Next step here would be really to add interactions with water. And basically, we are in a process of submitting a paper here. And the continuation of this work has been financed by the European Union within the first ever project in Europe to develop software for quantum computer. This is something we did together with Atos, and the project is called NASQC. Okay, now I come to the deep dive. So recently I submitted a paper which was a continuation of a patent. Really, I had together with my optimization team. This is the first patent I ever applied for, so it was a new experience for me. And in order to explain to you what this patent is about, I have to give you a deep dive about the algorithm which already existed before, which is called the quantum approximate optimization algorithm. So this is the optimization algorithm for noise intermediate scale for NISQ quantum computers. And what does this algorithm do? It calculates max cuts of a graph. And if you don't know what's a max cut of a graph, you're basically not probably the only one, because I also did not know what the max cut of a graph is when I started working on this problem. What you see, these three circles which you're seeing connected with two lines, this is what is called a graph. The circles are sometimes called edges, and are called vertices, and lines which you see are called edges. And then I give you two crayons. I give you the red and the blue crayon, and I ask you to color these three vertices into two different colors, such that the number of edges, the number of lines, let's say, which go between the circles is maximal. Circles of different color is maximal. Okay, now I'm going to show you what are the ways. So first, I show you what the colors do. So you can color the first two circles in red, and you can color the second circle in blue. And there is going to be one line going between the red and the blue, and you say that the max cut of this graph is 1. And there is an algorithm which does this for quantum computers. You assign every vertex to a single qubit, and you measure qubits at the end. And in this particular case, 2 qubits in this particular partition, 2 qubits would be in the state up, and 1 qubit would be in the state down. There are also more ways in which you can do something like this. You can say, okay, maybe the four left vertex is blue, and the other 2 vertices are red. This would mean that the first qubit in the algorithm was down, and second 2 qubits were up. And you can calculate a max cut being the number of lines which go between blue and red, which is in this case, as you see, 1. You can also do something like this, and you can say, okay, the middle vertex is going to be blue, and the vertices on the edge are going to be red. In this case, the max cut is 2 because I have 2 lines going. The cut is 2 because I have 2 lines going between the red and the blue, and this is the max cut of the graph. However, what was really problematic with the QAOA algorithm here is that for one type of, for one vertex, it requires 1 qubit to model such a graph bicoloring problem. So what we came up in Total, we came up with an algorithm which is exponentially more efficient in the number of qubits it uses. So instead of using 3 qubits, for this particular problem, you could use 2 qubits to solve this particular problem. And if you have a graph of 8 circles of 8 vertices, instead of using 8 qubits to solve this problem, you can use 3 qubits. and you had a graph of 32,000 vertices, instead of using 32,000 qubits to solve this problem, you can solve this problem with only 15 qubits. So this is the qubit overhead, which we are speaking exponentially less resources. And how this is done? It is done by adjusting the classical formula, which is called the Pohan formula for graph partitioning. So imagine that I give you a vector V, and this vector V is allowed to have +1 and -1. So in this particular case, the vector V would have dimensions of 3. It would have -1 on all of the blue ones and +1 on the red. So it would be 1, 1, -1, -1, 1, 1, 1, -1, 1. And by calculating kind of a vector matrix, vector product with the graph Laplacian, and I don't want to go into detail what the graph Laplacian is. If somebody wants to know, I'll say it later. And by maximizing kind of such a product, you calculate the max cut of the graph. And what we really found in total, we found a way how to do this exponentially more efficient than anybody has done before. And basically, at the end of the day, you derive with the formula number 4, which looks basically like this. And this formula number 4 is the quantum computing version of the Pohan formula. And it can be implemented with exponentially less qubits. What this allows us to do is basically allows us to partition graphs like this. So what you're seeing here, A, B, C, D, E, F is the largest graph ever partitioned on a gate-based quantum computer. So this is our in-house state-of-the-art. First, you can compare kind of GV is a Goeman-Williamson. It is a entirely classical solution. Qiskit MaxCat is a simulator of quantum computers, and IBM QKITO is an actual device. It's an actual quantum computer. And you see by the value of this MaxCat that the value which you obtain for actual quantum computers for these two graphs is far away from the value which you obtain on simulators or with classical methodologies, but this is due to quantum noise. So this is the reason. And we can go and do things which were unthinkable with quantum computing methodologies, and treat really large graphs which have in this case 128 nodes and get results which are 70% away from the exact result just by using basically IBM's Qiskit. This really brings me to the conclusion. I have basically gave you a bit of an overview of a flavor of our research in the quantum computing domain. I have shown you our state-of-the-art algorithm for graph partition. And what I didn't do, I did not have time to speak about the research in quantum error correction, about my Rana fermions. But if you're really interested and you want to know what we have, there's the archive reference, and you can go read there. Thank you. Now I would take questions.
Thank you, Marko, very much. It was really a teaser, as you said it would be, for all the aspects, including hardware, software, quantum algorithms, and for me, maybe the most interesting was material science part of the talk. So, okay, I will ask again.
I had to give a teaser because the paper is not really done yet, but I can tell you what the actual challenge is.
And I will ask the audience to ask the question in the chat in the meantime.
Yeah.
What I was interested in, as you said, it's over 100 electrons, so it's really a large system.
Large system, yep.
And it's running on this simulator or on the real?
It is what we have. We run it still on simulators, but it's runnable on real devices. You can run it on real devices.
Okay, and you said precision is what you are aiming for. And
yes.
That's really cool. Yes, and about the speed, is it comparable to some classical now solutions, or is it?
So I can tell you what you're seeing here. You're seeing CO2. This is this small molecule here, okay. And you're seeing it interacting with the fumarate. Fumarate is a part of this method organic framework, and I can tell you in number of time when we do fragmentation. The best calculation we can do on a simulator takes a full night to predict the bond dissociation curve of a fumarate interacting with CO2. Okay. This is on the order DFT would take. Maybe DFT on an actual actual regular laptop versus a kind of a cluster where we run our quantum computing simulation. But in respect of kind of how long does it take, it's comparable. I would say it's not we're not speaking about weeks, months, or.
Okay, and regarding some maybe resources we can find to start thinking about using quantum computation for material science. Is there enough information in the papers? Do you publish that kind of info? What do you recommend?
If you really try to get an overview, I'm going to advertise Qiskit because I think it's really good. You know, you just go, you open Python in your terminal. 5 minutes later, you have Qiskit, and 5 minutes later, you have access to actual quantum computers, and they have a lot of documentation there. So this is why it's good. You can also try Google Circ, which is also an amazing type of software, or Atos SQLM. What my team uses, we use everything. We have converters for one and another. They're all Python libraries. So you install Python, you go how to install Qiskit, you install Qiskit, how to install Circ, you install Circ. 10 minutes later, you're set really to try to treat lithium hydride on an actual quantum computer. So this is how long it takes. So it's not, you don't have to go and read papers, the documentation is really exhausting in the domain, so you can find it.
Thank you. Okay, let's see if we have some questions. Just a moment. Okay, everyone is saying very interesting, great presentation. And maybe someone wants to ask live.
Yeah, there was a question for chemistry. How can QC improve from O to the 2 power of n to O to the 2n? Can you explain a bit more? I mean, I can start from here if it's okay. Well, I can explain. The question is, how do you basically? Where do I start? I start with quantum mechanics. In quantum mechanics, the central object is called the wave function. And if I give you a wave function of a single electron, it's going to be a vector which has a dimension of 2 times 2. If I give you a wave function of 2 electrons, it's going to be a vector which has a dimension of 2 times 1. If I give you a vector of 2 electrons, it's going to have dimensions 4 times 1. If I give you 3 electrons, it's 8 times 1. So the size of the space on a classical computer exponentially scales with the size of the problem. And if I give you an n electron wave function, you would need to store a vector which has a dimensions 2 to the power of n in your classical computers. Well, quantum computers, if you want to model a free electronic wave function, you would only need 3 qubits for it. And you would not need to store it in your RAM memory. And if you want to model 1,000 electrons, you would need 1,000 qubits. But note, on a classical computer, you would need to store 2 to the power of 1,000. 1 to the power of 1,000 dimensions of vector for it. So this is what I meant by it. It's not real speed up. It's actually easier to store information about quantum objects in a quantum computer than in a classical device. Okay, and there was another on near-term noisy quantum computers, which applications or problems can gain most benefits? Optimization and chemistry. Optimization and chemistry, I would say, are currently the go-to things in NISQ. Material science also, but I would say less than chemistry. I would say the first customers of NISQ quantum computers are chemists and people doing optimization modeling.
Okay, we have one more. So I can just read, sorry. If you could give a link for more info about database access speedup.
I cannot give a link because I composed it myself from various papers. So this is something I made. I am not sure that's a comprehensive list of what is the speedup for each algorithm exist. Sorry, so I don't know of such a resource.
Okay, maybe they can contact you. And also, what is the difference in performance of quantum computers and GPUs when dealing with machine learning problems? That's probably.
I absolutely have no idea how to answer that, because I don't know so much about classical machine learning. I know a bit about classical machine learning, but not too much. I would say it's a big open question. Maybe this is the best way I could answer this. So recently, I looked at a classical algorithm, which is basically an algorithm to solve partial differential equations with neural networks. And somebody made a similar quantum algorithm out of it. So it's kind of a quantum neural network underneath. And we had a long meeting at Total Energies discussing where is really the quantum benefit coming from, or is there any? So, and in this particular case, we have an idea, we come to a conclusion that you have to test and try. So I cannot give a general answer for the question, is quantum machine learning going to perform better than quantum machine learning? I can just say that, for instance, for this problem with vibronic spectrum with quantum optical neural networks, it's mighty difficult to solve even with classical neural networks. They get stuck. You can find the same exponential overhead in resources when you need to model it.
So it's again about precision more.
No, it's about how big matrices, with how big matrices are you working, and how big matrices can your classical computer handle, versus a totally another kind of platform for doing linear algebra on a quantum device.
Okay, we have some links in the chat who wants to see. Sorry,
I have a couple of questions, if I may ask. Well, first of all, Marko, thank you very much for this wonderful presentation. It's really easy to follow, but it's at the same time, it is very deep. And what is valuable, I think, is, you're talking about the quantum computing for chemistry. And this is not, I find really very valuable to hear also this kind of use cases. And this leads me to a couple of questions that I would like to ask. When do you think that we'll be able to see the first practical use of quantum computers specifically for chemistry? And what do we need? Do we need some more qubits or error connection?
There are two ways in which you can answer. For either you need to think of a better algorithm, or you need quantum error correction. There were just recently a really nice paper from IBM. And okay, let me tell you what the problem is here. The problem is when you deal with electrons, you need 1 qubit for 1 electron. So on a classical computer, you have methodologies, chemists have developed methodologies for many years, which can trick 20, even 30 interacting electrons. And when you try doing the problems of similar size on a quantum computer, you start suffering from quantum noise. The energy which you calculate is less precise than it would be in a classical device. So you either need to think of a better algorithm, something which maybe uses less resources, or you actually need to wait for the next generation of processors. This can be either less noisy in these processors, or you would actually need quantum error correction. So how we do it with my team, it's always kind of a race. We recently solved a problem related to benzene. We applied a specific type of deformations to benzene, and then we computed it with a bunch of classical methodologies. This is entirely on the simulator, and then we see how do classical methodologies scale with respect to quantum computing. And I can say that our state-of-the-art algorithms for quantum computing, they are as good as the state-of-the-art classical methodologies, even on quantum simulators only. So you don't even need to go to an actual device to have something like that. So for actual devices, it's probably you're going to need quantum error correction or better qubits without quantum error correction. But on quantum simulators, today you can solve some really difficult problems and challenge classical methodologies even now.
But for example, when we take into account the roadmaps of companies like IBM, they're announcing thousands of qubits already in 2 years from now, and then the increase of this. And also when we take into account, for example, variational quantum algorithms, and more, maybe also from the chemistry point of view, well, to use some approximations. What is your feeling? When can we expect this? Is this in 2 years? It is in 10 years? What do you think?
Honestly, if IBM plans to produce the same type of error rates in their processor and make it with 1,000 qubits, is going to be useless. This is my opinion, because even today I have 65 qubits. I cannot use them. Why I cannot use them? Because it's too noisy. You know, I cannot put a 65 electron problem inside and get something valuable back so easy. So for me, it really either comes to turning to those architectures which have naturally less errors, such as the Honeywell architecture in the United States, which is much less error prone than solid state qubits, or waiting for solid state qubits to have quantum error correction, which is going to be somewhere around 2030. Maybe, but you know, it's always difficult to say because tomorrow somebody can come with a new algorithm, and bam, you have quantum speed up even now. So this is knowing what I know now, but if somebody invents a better algorithm, if somebody thinks of a way how to use these resources which we have better, then I wouldn't be surprised that in actuality, we have quantum advantage and quantum speed up even in a year or 6 months from now. It's an open question.
Yeah. So you mentioned solid state qubits. It means maybe there is going to be another alternative technology. Do you have some, one technology that you prefer, that you believe that will prevail in the end compared to superconducting qubits?
Oh, look, different. It's such a difficult question. It has so many layers to it. So superconducting qubits are great because they're accessible. So everybody can access it. Superconducting qubits are great because they're fast. So, you don't have to wait ages. This processor, it has gigahertz rates. But for instance, Honeywell has an architecture which is made out of ions in a ion trap, and they can move these individual ions and make them speak with one another. And this process is much less prone to noise. But the problem is that the processor has a kilohertz gate rate. So it's 1,000,000 times slower than a solid state qubit. And then, it's a question, do I want a faster processor, which is more prone to error? Or am I going to be okay with a slower processor, much slower, 1,000,000 times slower processor, but which is much less susceptible to error? So it depends on use case to use case. I would say I cannot give a general answer here. It really depends what you're trying to do. So maybe this is the spirit. Quantum computers today and quantum computers in the future, they're going to be different. If you want to take the quantum computer today and if you want to run a problem, the problem which you're running really has to be with the sledgehammer broken and reconstructed so it fits the quantum processors of today. But when you're going to do it in the future, in 2030, 2035, then you can do it in a hardware agnostic fashion. You take a problem, you put in the quantum computer, it's error corrected, it has no errors, and it works.
Yeah. And the last one, Marco, we can see on your screen CO2 capture. I think this is really very interesting, extremely important technology. To capture the CO2, well, that's, we are all talking about the climate change and the CO2 carbon dioxide impact. So you are studying actually how to use quantum computers for the capturing of the carbon dioxide.
Let me a bit tell you how this works. So basically, it's my team who develops these simulations with quantum computing, with simulators, quantum computers on an atomic level, I would say. And then we send this dissociation curve. So there's another guy who models all of this on a level of statistical physics. So he uses inputs from our codes to make his statistical physics model. And then when he makes the statistical physics model, then he's able to tell which technology do the guys in the lab have to use and how it's going to behave. So this is there are many layers again to it. This is just the one which is an atomic one.
And do you think that there can be a solution for this CO2 capture without quantum computer?
I don't think there's going to be a solution to any problem in chemistry without quantum computers in 10 years from now, because the promise of technology is such that it's going to be able to do something which classical computers are not really good at. It's going to be able to simulate nature on an atomic scale much better than classical computers can. So I don't think that any technology which relies on having input from simulating nature on atomic scale is going to be possible without quantum computing in maybe 5 years from now, maybe 10 years from now.
So we have to wait for you either to invent a new algorithm really to come to closer to this solution for the CO2 capture, or error correction and universal large-scale computer. Okay.
Yeah. Yes, I would say this is the take-home message. So either development on algorithmics, which works with current day quantum computers, or better quantum computers. But okay. I'm just saying that even now it's challenging. It's challenging. It's a game of which methodology works better. For instance, on certain type of problems, even now, we can only find the correct solution with simulators of quantum computers. Classical methodologies fail, all of them fail. And this is one problem which we're seeing, because it has something called van der Waals interactions between CO2 and the metallic cluster. Forget about all classical methodologies.
Okay, it's clear. Thank you very much, Marko. Katerina, maybe you can continue. I see
yes, one more question, if you don't mind. So also thank you for your reply, and wants to know, since we indicated that the wires need to cool to approximately absolute zero, can superconductors push up quantum computer development? Can you use quantum computers to find better superconductors, better materials for this purpose?
Okay, let me just read the question myself.
Okay, sorry. Yes.
I guess because of the noise. Can superconductors push? I mean, superconductors are pushing quantum computing developments now. The architecture in IBM, it's a transmon qubit. It's basically a strip of two strips of superconductor which are coupled to one another. So superconductors today are in the core of development of quantum computing, and this is not the only type of architecture which uses superconductors. For instance, qubits, hypothetical qubits based on Majorana fermions would also be also work with superconductors. So superconductors are in the core of current day quantum computing technologies. If not for qubits, then for making magnetic fields, which are adjustable and changeable. So quantum computing does not exist, or is really difficult to exist without superconducting technology.
Okay, but can quantum computer find better superconductor? That was the question. Can you use your quantum?
I am working on it. I can say in my own name. People are working in trying to model exotic state of superconductors with quantum computing. It was a bit pessimistic, our recent development. I would say that quantum computers of today are still not there to treat the full scale kind of phase diagram of a superconductor as good as a classical computer can do it. But again, same answer like to Sasha, either algorithm development or better quantum computers. So you can do two examples now for superconductors, but not kind of a full scale large superconductor with vertices.
Not large enough to make progress. Okay. Yeah. Thanks. And one more question from Ben Lee. For IonTrap, IonQ recently announced they have found error correction solution. Can you comment on that? Do you know what?
I did not. I mostly work with solid state qubits. I think IonQ's hardware is the one of which I know the least about, because I never got the chance really to play with it. I know that quantum error correcting solutions exist. You can even go today on IBM devices and try to implement a quantum error correction code of your own, a very limited one, limited in size. But the question is, how is this going to scale up if I put 1 million qubits on chip? This is the main question. right? So quantum, we know what we need for quantum error correction. We kind of understand what are the resources. We understand there is something called the toric code and something called the Venn-Plaquette model, which is ways of implementing quantum error corrections on an actual processor. We know what we need to do. It's just a question of how is it really going to pan out at the end? Are these theoretical, hypothetical proposals implementable on the large scale? And not sure what IonQ has, but they probably have something which is, 4 or 8 qubit error correction. You can also do this with the IBM devices. The question is, I give you 1 million qubits, is it still going to work in the same way?
Thank you. If we have some more questions, maybe, or comments. Okay, I think that's all for now, but thank you once more. It was really interesting and really teasing for everyone, I think.
Thank you. Thank you so much. And sorry for giving a teaser talk, but in the time limitation, I could have, if I wanted to speak about everything in detail, it's probably 6 hours. Yes. So I kind of needed to make a selection, and I probably missed a lot of other great work.
So, okay, that's, I think, there's also a question, can we get the slides? You will have the recording of this.
I'm not at liberty to disclose slides. There is a recording, and all rights are reserved on the slides, so I'm not free to share them.
Yeah, that's important to say. Okay, thank you once more, Marco, very much. And let's invite everyone to join again in Quantum Serbia meetups.
Thank you. Bye-bye. Have a nice day.
Thank you.